All right, today we're tackling a classic A-level maths challenge. We're going to see how two powerful techniques can come together to create one really elegant solution. Okay, so here's the beast we're up against. Just looking at it, it seems like a total nightmare to expand, right? And to make things a little spicier, it's an improper fraction. That means the highest power of x on the top is the same as the bottom. But you know what? Don't worry, we've got the perfect set of tools to break this thing down. We're talking about partial fractions. Think of it like this. You've got this super complicated cake, and what this technique does is it lets you break it all the way back down to its basic ingredients: flour, sugar, eggs. It just makes the whole problem so much easier to handle. And this checklist? This is basically our roadmap. See those highlighted bits? Case 1 tells you exactly what to do for simple, distinct linear factors. Case 2 is for when you've got repeated factors. And Case 3 even handles quadratics. So for any problem, you just find the case that matches, and you've got your structure ready to go. Okay, let's see how this actually works with a quick example. Here, the denominator has two different linear factors, right? We've got x minus 1 and x plus 2. Looking back at our roadmap, that's a perfect match for case 1. So we're going to set up our partial fractions to look like a over x minus 1 plus b over x plus 2. So once we set our original fraction equal to a over x minus 1 plus b over x plus 2, we can go ahead and solve for a and b. A common trick is to plug in some clever values for x that make things disappear. And just like that, one really messy fraction turns into these two super simple ones. See? That's the real magic of decomposition. It makes the problem manageable. All right, so now we've got our simple ingredients. What's next? Well, we need a tool that can expand them out into the series we're looking for. And that's where the binomial expansion comes in. This thing is an absolute powerhouse. It takes our simple little fractions, which remember we can just write as something to the power of -1, and it explodes them out into an infinite series. And this right here is the golden formula. Now, the most important thing to remember, and I mean the most important thing, is that the expression has to be in this 1 plus something format before you can even think about using the formula. For our problem, we only need to go up to the x squared term, so we'll just be using the first 3 terms of this series. Easy enough, right? Okay, let's head back to our original problem and see how these two tools build on each other. We are totally ready to combine them now and solve this thing step by step. Okay, step 1, we apply our decomposer. Now, remember how I said our original expression was an improper fraction? Because of that, our very first move has to be algebraic division. When we do that, we get a whole number, in this case 1, plus a proper fraction that we can actually work with. Then we can decompose that leftover fraction. The end result is this much, much friendlier form: 1 plus 6 over 2x plus 1 plus 5 over 2 minus 3x. Now it's time for our expander. We're going to take each of those two simple fractions and get them ready for the binomial expansion. And what does that mean? It means we have to carefully rearrange them into that super crucial 1 plus x to the n form. Once they look right, we can just apply the formula and get the series expansions we need, right up to that x squared term. And for the grand finale, we just put it all back together. We take that 1 from our initial division, we add in the 2 new series we just created, and then we just group up all the like terms. All the constants go together, all the x terms go together, and all the x squared terms go together. And there it is. The coefficient of x squared is 29.625, or if you like fractions, 237 over 8. We did it. We took that monster problem, broke it down, and built it back up into a simple answer. You know, this two-step process is incredibly versatile. But what happens when the problems get even trickier? So let's take a look at question 6 from the exercise. This one's got a repeated linear factor in the denominator. See that, x minus 2 squared? That adds a little twist to our partial fraction setup. It means we're going to need a term for x minus 2, but also another one for x minus 2 all squared. But check this out. The core strategy, it stays exactly the same. First, we decompose the expression. This time, it breaks into 3 simple fractions. Then, we expand each of those pieces using the binomial theorem. The fundamental method just holds up beautifully, even with this extra bit of complexity. So, after all that, what's the crucial process you should really take away from this? It really boils down to this 4-step strategy that will turn a ridiculously complex problem into a manageable process every single time. 1. Decompose, using your partial fraction rules. 2. Rearrange each piece into that k times 1 plus ax n form. 3. Expand each term using the binomial theorem up to whatever power of x you need. And 4. Combine everything back together to get your final answer. Decompose, rearrange, expand, combine. You master those 4 steps, and you can take on any problem just like this. You know, this combination of techniques really is a perfect team, a mathematical power couple. And it kind of leaves you wondering, right? What other areas of math have tools that pair up so powerfully to make something that seems impossible totally possible?